Okay, I must admit, I personally consider this to be a small win, because holy crap. In a nutshell, what I have achieved here is being able to read the analog voltage from this little 10K potentiometer into one of the analog pins, and as you can see, if I turn, there we go. There's an internal wait timer that waits a certain amount of seconds based on the position of the potentiometer. But the reason why I consider this to be a small win in my book is because I've been able to figure this out by myself by doing nothing more than just reading the data sheet and looking at the sample projects that were provided by the programming environment software developers or by the microcontroller developers. Just for frame of reference, when you're working with Arduinos, you have this ginormous wealth of information that you're basically standing on the shoulders of billions of giants at that point. Everybody has example projects, everybody has libraries, but when it comes down to less mainstream microcontrollers like this teeny tiny CH32V003 microcontrollers, you are kind of left by yourself. So I've been reading up. Take a look up there. ChatGPT had been absolutely useless in helping me make sense of this. So much for artificial intelligence. But I have been able to take a look at there's a abbreviated pinout which tells me what all the abbreviations mean. For example, the analog to digital converter could be abbreviated as ADC or A7. So just kind of observing this allowed me to see a pattern. For example, okay, so A2 must be ADC channel 2, and A7, this is the ADC 7, and I guess is there another one? Maybe. Maybe not. So, A5, analog 5. And in hindsight, looking after I've set this up, it blows my mind how actually simple it is, and how frustrating it is that the most difficult hurdle that I had to overcome is my chronic inattentiveness to detail. And by that I mean I found a example project that you can download for these microcontrollers, and there was a nice ADC example project from which I had quite literally just borrowed two functions. We have the ADC function initialize and get ADC value. I just copy pasted these two functions. All I had to do is just change the port. I think it was already port C, but I had to change the pin. And this is where some of my misconstrusions of the red information came from. I figured, okay, well, is it pin 4 as in, is it pin 4, which doesn't make sense because it's VDD, but then we have PC4, and then we also have, I think there's like a bunch of other 4s somewhere scattered all over this definition. In the end, if this said pin 4, then this meant GPIO port C channel 4, which would be, excuse the phone noises, but this will basically be port C channel 4, which is actually analog channel 2. So it's one of those things where it might be a little frustrating getting into this sort of down and dirty bit flipping, programming my controllers through directly addressing certain ports and whatnot, because I'm coming from the Arduino infrastructure, which is where I'm like super pampered with all these pre-made functions, pre-made libraries. Just run this one function, provide 5 parameters, and bam, it just runs. And the worst part of setting this up was quite literally realizing that I have this entire ADC function in it, which sets up the analog port for me, and yet I didn't bother to actually execute this function in the main function of the code, which means it basically did quite literally nothing. Big old zilch. And of course, as soon as I populated it, just immediately started working. And how many of these lessons am I gonna have to learn? I fear they will never stop. So I got it. I got the analog to digital converter running, which means, well, what's all this for? Well, as I mentioned before, my plan was to use these little 4-pin switches to allow the user to set the channel of which MIDI channel they want to read the data from. But then it kind of got me thinking, it will work, but is it really user-friendly? Is it easy to understand? I mean, realistically, if I implement that system, I will have to rely on the user knowing how to build up a binary value, which it's not difficult, but you know, there's no shortage of musicians who are like, I just want to make music. I don't want to learn a whole new language or a whole new number system. And to be honest, like in the beginning, I probably was in the same sort of realm before I got into electronics experiments. So, okay, let's say we're not using those little 4-pin flip switches. How else are we going to tell the user what channel they're working with? So another option would be to use something like this, which is a switch that I'm really, really fond of. It's a rotary switch, so it has a whole bunch of pins on the back, and it allows you to bridge one of the center pins, and based on the position, oh, that's so satisfying. Based on the position of the switch, it will determine the which connection all of these pins are bridged. So here's the deal. The way I figured, the only problem is that this type of switch, as satisfying as it sounds, these are surprisingly expensive. And I think it's because they're not as mass-produced, perhaps. If I was building like a, I don't know, $1,000 piece of hardware, then sure, you know, spare no expense. This thing is pretty damn sturdy, right? But considering that we're building a MIDI breakout board and one that isn't really programmable, this gets me thinking if this is really cost effective, because I'll need 16 of these, right? We got 16 channels, 16 MIDI channels to manipulate. I'm gonna have to have 16 of these. It's a little expensive. I think I've seen these things go for around $6, so 16 times 6, that's almost $100 in just these switches alone. So this got me thinking, okay, how do I keep the knob part but make it a little bit more cost affordable or cost effective? Well, I mean, these knobs work, right? They don't have the snappy feel to them, but at the same time, these are like, what, $1 a piece? So the idea I got was to see if I can make one of those knobs to be snappy. So the ultimate question is really, how do I keep the clicky bit but maintain the cost affordability of the regular potentiometers? And the general idea was to experiment with manufacturing my own almost like a divider dial that would be mounted as almost, I would say, as a cap or as a knob. And the idea there is that it's a disc containing, I would say, what, serrated teeth? Like this. Right, so it's basically a whole bunch of teeth, and then we have the knob part. This is the part that the user twists. It has a little needle that indicates where you are, and it too has serrated teeth. Maybe some sort of a spring in between. This is obviously a gross oversimplification, but the idea is that the spring would keep the knob in tension, and then what you would do is when you spin this around, the serrated teeth almost lock in place, and when you spin it around, you'll have a bit of an action where the tooth kind of climbs over one another, and then when it overcomes the top, it would effectively snap into the next ridge, so to speak. It's always simple in theory, but the actual construction, I'll have to experiment. I'll see how I might be able to pull it off, but there's benefits to this particular solution. First of all, I get to use the, $1, $2 knobs. Second of all, I think experience might be pretty good for something like this, basically engineering my own type of knob. And third, it actually frees up, in this case, like 2 or 3 more pins for me to be able to do something with. I don't know, some sort of indicator, some data line maybe. So having extra pins is always good, so I guess we can work with that. Who knows, if I have 3 pins, I might be able to hang a shift register, and then have 2 shift registers in series and light up. Ooh, maybe. Basically have, if you have the front view of the knob, then we have the indicator, and then let's say this is channel number 10. Right, maybe I can make the number 10 light up, right? And we got channel 11, 12, 13, 9, 8, right? So whenever you twist this knob to the number of the channel, it'll make that channel light up. I have experimented with making aluminum panels that have light up lettering. It's not exactly the cleanest look. This, I would say, is the most successful result. This was made from clear see-through resin. This was mixed with a bit of a dye, white dye. These ones are kind of failed experiments. I tried to vacuum pump them. So realistically, if we're looking at, let's see, if we're looking at a light up effect, it will obviously not be done with this kind of LED, but it does technically light up if we're in a dark enough environment. And then we get more flat area effect LEDs, because this type of LED has a rounded cap, which means it focuses the light on a much more single point, like a lens. As long as I'm making the custom dial, I might as well make it nice. So having the serrated edges will allow me to basically divide the entire range of the potentiometer into like 16 regions, 16 steps, maybe 17, so that I could keep Omni as a potential channel option. So that might be nice. And I am definitely aware of these rotary encoders, which, as you can see, they quite literally do what I am describing I want to do. But I mean, I'd have to figure out how to get the rotary encoders data reading those pulses, those values, which eventually I have to do that anyways, but I don't know. I think this was more interesting. I think it might even be more satisfying to have that click and do it for experience, right? Do it for the experimentation's sake. So we'll stick to this, see how it goes, and wish me luck on this little experiment. Other than that, the key achievement for today is being able to read the analog data from this potentiometer, and I pretty much had no help, no external help, being able to figure this out by myself. I think that's a pretty good achievement to put on my self resume. Right, kudos. Thanks for checking up.